In section 3.2, we're going to talk about differentiability, which means the ability to have a derivative. Derivatives fail to exist at, first of all, corners. An example is y equals absolute value of x. If we graph y equals absolute value of x, it looks like a V. It should be a straight line. Derivative will not exist at the very bottom point right here. Now, a derivative is the same as the slope of the tangent line, and we could draw a tangent line at this point, in other words, a line that would touch the point only one time. But the problem is we can draw multiple lines that do that, a whole bunch of tangent lines that would cross at one point to the curve. So since we can draw a whole bunch of them, that means it doesn't have a derivative. It doesn't have a tangent line at that point. Another one is a cusp. For example, y equals x to the 2/3, which curves to 0 instead of going straight. Curves, touches, and then curves again. So this one should be perfectly straight. That's what absolute value is. And this one curves to the point where we don't have a derivative. A derivative doesn't exist at any of the discontinuities. For example, removable, infinite discontinuities, or jump discontinuities. You will not have a tangent line at that value. Vertical tangents. If we have a curve that curves so much that it becomes vertical, curves straight up, and then curves again, let's say that one, there would not be a tangent line at that value right there where the tangent line would be vertical. It wouldn't exist at this value. Find where f is differentiable for f of x equals, well, this function. Functions won't have tangent lines and it won't be differentiable where there is a discontinuity. So if we factor the top here, we get x minus 2, x squared plus 2x plus 4. And when we factor the denominator, we get x plus 2, x minus 2. The function is differentiable everywhere except for 2 and negative 2. There'd be a hole at 2. There'd be a vertical asymptote at negative 2. So find where f is differentiable from negative infinity to negative 2, union with negative 2 to 2, and then union with 2 to infinity. Show f of x is not differentiable at x equals 1. In order to have a derivative, you must have a tangent line at this point. So we certainly don't have a tangent line because we have a tangent line that looks like that for the left function, and we have a tangent line that might look like that for the other function. So we already know that it's not differentiable at 1, but we have to show that. And so we have to find the slope of the tangent line on each side and show that it is not equal. So we have the limit as h approaches 0 of, let's call this side f of x, and we can say that this side is g of x. So we have the limit as h approaches 0 of 1 plus h minus f of 1 over h. So we have the limit as h approaches 0. Let's see, 1 minus 1 will go away, and then we'll have h over h. So we have the limit as h approaches 0 of 1 will equal 1. There's the left-hand limit. And this as h approaches, So we have a limit of 1 on the left-hand side. And on the right-hand side, we have the limit as h approaches 0 of f of 1 plus h, or g of 1 plus h in this case. So we have 1 over 1 plus h minus f of 1, or g of 1 that is, over h. So we have the limit as h approaches 0 of, well, we got to get rid of this complex fraction, so we're going to multiply everything by 1 plus h. 1 plus h. So we're going to have 1 minus 1 plus h, in parentheses, all over h times 1 plus h. So we have the limit as h approaches 0 of the 1 minus 1 is going to cancel. So we have negative h over h times 1 plus h. The h's will cancel, leaving negative 1 over 1 plus h. Finally, we're going to plug 0 in, and we'll get negative 1. Now we've shown that there's no derivative at 1 because the slope of the tangent lines are different. If they were the same, then it would be differentiable at x equals 1. If f has a derivative at x equals a, then f is continuous at x equals a. In exercise 5 through 10, the graph of the function over a closed interval d is given. At what domain points does the function appear to be a differentiable? Well, let's look at this graph. We have a corner, we have a jump discontinuity, and a removable discontinuity. So where is this thing differentiable? Well, it's more interesting to talk about where it is not. It's not differentiable at 1, it's not differentiable at 0, and it's not differentiable at 2. So where is it differentiable? Well, from, it's actually, we're going to include -2. -2 to -1. We got to skip over -1. -1 to 0. Have to skip over 0. Union. 0 to 2. And then finally union with 2 to 3. Continuous but not differentiable. So it's not differentiable at these three values, -1, 0, and 2. So it's not differentiable at those three values, but it's still continuous at -1, even though we don't have a derivative, the line never broke. It is continuous there, so x equals -1. C, neither continuous nor differentiable. So it's not differentiable and it's not continuous either. And those are at 0 and 2. X equals 0, x equals 2.